Hello, chemistry students. Mr. Niego here with a quick video on mole conversions. So in the previous video that I uploaded, we talked about dimensional analysis. When we talk about mole conversions, we are doing the exact same process, except for now, instead of using other units of measure like feet and meters and seconds, we're using the mole and the three conversion factors that come out of it. So if you're looking at the sheet, these three things that I'm putting a box around, these are our conversion factors. Now, myself, I'm more of a visual learner. So I call this the mole map. And I'm going to take these three conversion factors and I'm going to apply them to the mole map. So in the middle, I have moles. And then from moles, I can go to particles. And when I talk about particles, a particle is either an atom or it could be the number of molecules. So when you see the word atoms or molecules, we're talking about particles. Okay, the mole will also help me to convert to mass and to volumes of gases at STP. And STP is just environmental conditions. It means a standard temperature and a pressure. So if I look at my conversion factors, we have three. So when I'm going from moles to particles, I have 1 mole, and I'm going to use MOL for mole to simplify it, is equal to 6.02 times 10 to the 23rd particles. When I go from moles to mass, my conversion factor is 1 mole is equal to the molar mass, and I can find that on the periodic table. And last but not least, when I go from moles to volume, 1 mole is equal to 22.4 liters. And remember, that is only for gases and only when we're at standard temperature and pressure. So by knowing these three conversion factors, and once again, you have to memorize these, you need to know them or be able to apply them. By knowing these three conversion factors, we can convert between particles, moles, mass, and volume. And essentially, that's what this worksheet does. So each section of the worksheet is going to take a different mole conversion. So let me just make a copy of this because we're going to use it a little bit later on. So I'm going to come down to section number 1. So in section number 1, we are using moles to particle conversions. So let's look at question number 1. So in question number 1, it says how many moles of magnesium is 3.01 times 10 to the 22nd atoms of magnesium. So as we start getting into more complex math problems, it's really important that you understand what the question is asking and what is given to you in the problem. I mentioned this in class, but we can actually annotate our questions by underlining what's given and circling what's being asked for. So in this problem, I'm given 3.01 times 10 to the 22nd atoms of magnesium, and I'm being asked for the number of moles. So how many moles of magnesium? So by that simple annotation, I'm quickly able to understand what they're asking me to do. So let's map this out. So I'm going to go ahead and paste our mole map right here. So essentially, what are we doing? Well, I have atoms of magnesium. So where do atoms of magnesium fall? Well, that would be particles. Well, I'm right here. And what am I being asked for? I'm being asked to go to moles, which is down here. So I'm converting from particles to moles. So my conversion factor would be 1 mole equals 6.02 times 10 to the 23rd particles. Now, I highly recommend that you actually write out your conversion factors. So my conversion factor is equal to 1 mole. So 1 mole of what? 1 mole of magnesium, Mg, is equal to 6.02 times 10 to the 23rd atoms of magnesium. Notice this conversion factor comes directly from this mole math. I'm not worried about the 3.01 times 10 to the 22nd right now. All I'm doing when I'm looking at my conversion factor is I'm picking one of the three that are listed. And actually, let me move my video so you can see the last part. Okay, so I'm only picking one of the three conversion factors. These three conversion factors you need to commit to memory and be able to use them. Okay, so for me, when I'm solving this using dimensional analysis, once again, dimensional analysis is a way that we can convert from one unit to another using conversion factors. I use what's called the railroad track method. So in the railroad track method, I'm going to draw a long line. It's called the cancellation line. Any units that are above the cancellation line and below the cancellation line that are the same, I can cancel them out. So when I do the railroad track method, I draw a long line. In the upper left-hand corner, I put what's given. In this case, I was given 3.01 times 10 to the 22nd atoms of magnesium. I draw a vertical line to separate what's given from my conversion factor. Okay, so in my conversion factor, if I have atoms of magnesium above my cancellation line, to cancel those out, that unit out, I want to have atoms of magnesium below my cancellation line. So I want to have 6.02. So I'm just applying this conversion factor. So 6.02 times 10 to the 23rd atoms of magnesium. And I'm going to have 1 mole of magnesium on top. And notice, because I have atoms of magnesium above my cancellation line right here, and because I have atoms of magnesium below my cancellation line here, those units will cancel out. And I'll be left with moles of magnesium. And if I check what I have circled, that's what I'm looking for. Okay. So to solve this, I'm going to use my calculator. So hopefully this will work. I'm going to switch to a different screen. Okay. So there's a specific way to put in scientific notation into your calculator. So this website it shows a TI-84 plus calculator. So very similar to the ones that you're going to use in my classroom. So if I go back, if you remember from my previous video, if I have a number in the numerator above my cancellation line, I multiply. If I have a number below my cancellation line, I divide. If I have a 1, I neither multiply nor divide, because anything multiplied by 1 is itself, and anything divided by 1 is itself. So if I see a 1, I just forget that it's there. So in this case, when I type this into my calculator, I'm going to put in 3.01 times 10 to the 22nd divided by 6.02 times 10 to the 23rd. All right, so doing that on the next page, I'm going to have 3.01. Now this is where it gets important. So there's an actual button for scientific notation. The scientific notation button is the EE button. It's where the comma is, and it's above the number 7 button on the calculator. So when I'm typing in scientific notation, watch my keystrokes. I'm going to type in 3.01, and then I'm going to hit the second function, and then the EE button. And notice that I have an E. That E represents times 10, and the exponent for my scientific notation was 22. So once again, if I'm writing 3.01 times 10 to the 22nd in scientific notation using my calculator, I'm going to type in 3.01 second EE 22. Right now, I'm going to divide that by 6.02. Once again, second EE 23. So 6.02 times 10 to the 23rd. And when I hit enter, I'm going to get 0.05. So that would be the number of moles of magnesium that I have. So that is my answer. You may see it done a different way. So in the videos, they used fractions instead, but it ends up being the same thing. So the other method would be to do this. So I take 3.01 times 10 to the 22nd atoms of magnesium. And then I would multiply that by my conversion factor. Now, when I do it this way, I think of this as a fraction over 1. Why? Because 3.02 times 10 to the 22nd atoms of magnesium over 1 would be 3.01 times 10 to the 22nd atoms of magnesium over 1 would just be 3.01 times 10 to the 22nd atoms of magnesium. So sometimes it's easier to think about it over 1 to help align your conversions. I'm going to use the same conversion factor. So 1 mole of magnesium is equal to 6.02 times 10 to the 23rd atoms of magnesium. Because I have atoms of magnesium in the numerator and atoms of magnesium in the denominator, they cancel. Once again, we're just multiplying by fractions. So I'm going to multiply any numbers in the numerator, divide by any numbers in the denominator. So I get 3.01 times 10 to the 22nd divided by 6.02 times 10 to the 23rd. And the unit that I have that's not canceled is moles. So my answer would be moles. So it comes out to the same result. So that's moles to particle conversions. So given that, given the other videos, you should be able to answer questions 2, 3, 4, and 5. Okay, let's look at moles to mass conversions. So let me go ahead and I'm gonna paste our mole map. And I'm gonna move my image so that I'm out of the way. Okay. All right, so we're gonna do question number 1. So in question number 1, the question is how many moles in 28 grams of carbon dioxide, CO2? So just like I did before, we're gonna underline what's given. In this case, I'm given 28 grams of CO2. And I'm gonna circle what I'm being asked for. So I'm asked for how many moles. If I look at my mole map, where am I? Well, I'm given grams, which should be a measure of mass, and I'm asked to find moles. So I'm going from mass to moles. So the conversion factor that I'm going to use is I'm going to use 1 mole is equal to the molar mass. Okay, so how do I find the molar mass? Well, on the molar mass, what I'm going to have to do is I'm going to have to use my periodic table. So the mass on the periodic table, so looking at carbon. So according to the periodic table, carbon has a mass of 12.01. So 1 carbon atom would have a mass of 12.01 AMU. But we're not talking about masses of single atoms. We're talking about the mass of a mole of carbon. So the unit for this would be grams. For oxygen, oxygen has a mass of 16.00 grams. But if I look at my chemical formula, how many oxygens do I have? Well, I have 2, CO2. So I have to multiply this by 2. So that will give me 32 grams of oxygen. When I add the 12.01 with the 32.02, and actually let me just move this over so we can get everything aligned. When I add these up, I get 44.01 grams. So that would be the molar mass of carbon dioxide. So for my conversion factor, once again, it's a good habit of writing down your conversion factors. 1 mole of carbon dioxide, CO2, is equal to the molar mass, which is 44.01 grams of CO2. From here, I just set up my dimensional analysis. So I'm going to draw my cancellation line. In the upper left-hand corner, I'm going to put what I'm given. In this case, I'm given 28 grams of CO2. I'm going to draw my vertical line to separate what's given from my conversion factor. Since I have grams of CO2 above the cancellation line, I'm going to take this conversion factor and I'm going to put my value for grams of carbon dioxide below the cancellation line. So that would be 44.01 grams of CO2. And then on top, I'm going to put 1 mole of CO2. Grams of CO2 cancel. And I'm left with moles of CO2. Now to solve, anything in the numerator or above the cancellation line, I'm going to multiply. Anything on the bottom, I'm going to divide. If I have a 1, I'm going to disregard it. So using my calculator, I'm not going to use the graphing calculator because we're not using scientific notation. So I'm just using my basic calculator here. So I'm going to take 28 divided by 44.01. And I'm going to get 0.636 moles of CO2. Okay, so that's my answer. And once again, I could do it using the other fraction method. So that would look like this. So it would be 28 grams CO2. Actually, let me delete this real quick and give us a little more room. So it'd be 28 grams CO2 times 1 mole CO2 over 44.01 grams CO2. Once again, I like to put that as a 1, and then my grams cancel, and I do the exact same thing. So 28 divided by 44.01, and I get the same answer. Okay, so far we've talked about going from looking at the top. So we've looked at going from particles to moles, between particles and moles, and mass and moles. So the next problem deals with moles to volume conversions. So let me go ahead and I'm going to paste our mole map, and I'm going to move my face out of the way. All right, so just like we did before, these problems are like almost identical. Like once you understand the process, it should be pretty easy to keep doing these over and over and over again. So question number 1 is what we're going to work on. And it says determine the volume in liters occupied by 0.030 moles of a gas at STP. So I'm going to underline what I'm given. So 0.030 moles of the gas at STP. And I want to find volume in liters. Well, if I look at my mole map, I'm going between moles and I'm going to volume of a gas at STP. If I look at my conversion factor is 1 mole of a gas is equal to 22.4 liters. Now, I could have chosen any gas. It could have been oxygen, it could have been hydrogen, it could have been whatever. The big thing for this is when we talk about volumes, it's all about using gases. So I'm going to use my cancellation line. I'm going to put what's given. So 0.030 moles. And I'm going to draw my vertical line to separate my given from my conversion factor. Since I have moles in the numerator above the cancellation line, I need moles in the bottom. So I'm going to write 1 mole on the bottom and 22.4 liters on the top. My moles cancel, and I'm left with the unit of liters. As I said previously, if it's above the cancellation line or if it's in the numerator, I multiply. If it's in the denominator, divide. If it's a 1, I don't worry about it. So in this case, I'm going to do 0.030 times 22.4, and I get 0.636 672 liters of some gas. So that would be my answer. As with the other videos, I could do it in fraction form. So it'd be 0.03 moles times my conversion factor, which is 22.4 liters over 1 mole. My moles cancel. Once again, I like to put this over 1 so it looks like a fraction and I can align everything. So it'd be 0.30 times 22.4 liters. I get the same results, should come out to 0.672. I don't really care which way you use, as long as you get the right answer. Okay, so up until this point, we've looked at each of the conversion factors. So we've gone from particles to moles, mass to moles, and volume to moles. And the last part, we're going to talk about mixed problems. So a mixed problem is one where I'm going to be using 2 conversion factors. And let's look at, yeah, here we go. We're going to do number 2. So I'm going to copy and paste my mole map. We'll make it a little bit smaller. I think I can do that. There we go. There's my mole map, a little bit smaller. And I'm going to face it out of the way. Okay. So in question number 2, it says you discovered that the head of a match contains 1.6 grams of sulfur. How many atoms of sulfur does a match contain? Does the match contain? So what am I given in the problem? Well, I'm given 1.6 grams of sulfur. And what am I being asked for? I want to know how many atoms of sulfur. So if I map this out, and once again, this is why I think it's really important for you to draw out the mole map. I think it helps in figuring out your conversion factors. Once again, I'm a visual learner, so it really helps me. So if you're a visual person too, I would suggest at the beginning of any quiz or any test that you have this mapped out or drawn out so that you can reference it. So where am I going? Well, I have grams, so that's down here at mass. And what do I want? I want atoms, which is up here at particles. So if I look at this, there's no way that I could go from mass to particles directly. I don't have a conversion factor that takes me there that has mass and particles. So what I have to do is I have to do this in 2 steps. I have to convert from mass to moles, and then I have to go from moles to particles. So in these mixed problems, it may be that you have to use 2 conversion factors. So what are the conversion factors that I have? Well, the first conversion factor that takes me between mass and moles is 1 mole of sulfur, which is S, is equal to the molar mass of sulfur. Well, sulfur is easy because it's just an element. So if I look at my periodic table and I look at sulfur, sulfur has a molar mass of 32.07 grams. Okay, so that's my first conversion factor. Okay, so that takes me from mass to moles. Well, I still need to add a second conversion factor, one that will take me from moles to particles. And this conversion factor is 1 mole of sulfur is equal to 6.02 times 10 to the 23rd. In this case, we're talking about atoms of sulfur. Okay, so that's my second conversion factor. So I have to apply 2 for this problem. All right, so now that I have my conversion factors listed, now it's just a matter of doing dimensional analysis and applying everything. So I'm going to draw my cancellation line. I always start in the upper left-hand corner of what I'm given. In this case, I have 1.6 grams of sulfur. Okay, I'm going to apply my first conversion factor. So 1 mole of sulfur is equal to 32.07 grams. Since I have grams above the cancellation line, I want grams below the cancellation line. So 32.07 grams of sulfur on the bottom, 1 mole of sulfur on the top. My grams of sulfur cancel out. So I've used this conversion factor. If I were to stop here, I would have only done this first conversion. I would know how many moles of sulfur I have. That's not what I want. I want to know how many atoms. So now I have to apply a second conversion factor. So since I have moles above my cancellation line, I need to put moles on the bottom. So 1 mole of sulfur. So now I'm looking at my second conversion factor. And on top, I'm going to have 6.02 times 10 to the 23rd atoms of sulfur. My moles of sulfur cancel. And right now, the only unit that I have that's not canceled out is atoms of sulfur, which is, if I look over at what I have circled, is what I'm being asked for. When I solve this, I'm going to do the exact same thing that I've done on the previous problems. If it's in the numerator, I'm going to multiply. If it's in the denominator, I'm going to divide. So 1.6 divided by 32.07 times 6.02. And remember, I'm going to use the EE function to be able to put this in scientific notation. So 6.02 times 10 to the 23rd. Sorry, that looks like a 2. This should be a 3. And I get 3.00. On your calculators, it probably says E to the 22nd. What that really means is I have 3.00 times 10 to the 22nd atoms of sulfur. If you leave it with an E, that is incorrect. That is not the correct way to write scientific notation. You have to write times 10 to the 22nd. Remember that E, when you see E, you should be thinking times 10 to the 22nd. I could also write this using the fraction method. So it would be 1.6 grams of sulfur times 1 mole of sulfur over 32.07 grams of sulfur times 6.02 times 10 to the 23rd atoms of sulfur divided by 1 mole of sulfur. Moles of sulfur cancel, grams of sulfur cancel. So can I think about this over 1, and then I solve it the same way. If it's in the numerator, I multiply. If it's in the denominator, I divide. At the end of the day, I don't care which method you use. What I care about is that you're showing your work and you're giving me an answer. So we've practiced using all of the conversion factors. So the mole concept is nothing different than the dimensional analysis practice that you did before. The only thing that is different about it is that we now have 3 conversion factors that you need to commit to memory. 1 mole is equal to 6.02 times 10 to the 23rd particles. 1 mole is equal to the molar mass, and 1 mole is equal to 22.4 liters. We're actually making it more simplified because instead of all the conversion factors that you could use, you only need to know 3. I hope that was helpful. If you have any questions, please make sure that you send me an email. Thanks again.